All right, section 3.7 is called Rates of Change in the Natural and Social Sciences. I don't want to spend a ton of time in this section just because I feel like a lot of what's in here is things that we've already talked about. And we're going to be talking a lot about rates of change in section 3.9. We're going to skip section 3.8, just a heads up, and so I'll go to 3.9 after this. In 3.9, we'll look at what's called related rates. Okay, so I thought the best way to handle this section would be just to do some problems that are in the book here. I'm on page 233, and problem 8 was one problem I liked on that page. It says in problem 8, if a ball is thrown vertically upward with a velocity of 80 feet per second, then its height after t seconds is given by the equation that you see there. Okay, part A, what is the maximum height reached by the ball? All right, well, let's get that here. So here's my function s, which is a function of time, and we want to know the maximum height of the ball. Well, in algebra, you can describe this curve as a quadratic that is facing downward, and so you could find the vertex. That's one way, but another option to think about it is like this. So the ball is going to be heading upward with a velocity, right? And then it's going to change direction and then fall back to Earth. Now, at that moment where the ball has reached its highest point, the velocity is going to be 0. So, why don't we calculate the velocity function? We'll set that equal to 0, and we can know that time when the velocity is 0. Once we have that time, we can then plug that into the position function to know the height of the ball. Well, v of t would be just a power rule on these two terms, 80 minus 32t. And if I set that equal to 0 and solve for t, I get t equal 80 divided by 32 is 5/2 if you reduce. Okay, so it looks like after 2.5 seconds have gone by, the ball is going to be at its highest point in the air, and at that exact moment in time, it's going to be changing directions from upward to downward and falling back to Earth. Now, to know the height of that ball, I would just plug 5/2 into my function here and simplify. So 80 times 5/2 minus 16 times 5/2 squared, you should get 100 feet when you do that. One nice thing about doing the calculation like this is so that you don't have to go back to algebra and remember what's the formula for the vertex on a parabola. Okay. Part B is the next one here. So in part B, it says, what is the velocity of the ball when it is 96 feet above the ground on its way up and then on its way down? All right. Well, let's find the time at which the ball is going to be at 96 feet in the air. So if I set the position equal to 96 feet and then solve this equation for t, you can factor out a negative 16 and then divide by that number. That'll make the numbers a little bit nicer here for factoring. T squared minus 5t plus 6 equals 0. That's going to factor nicely on the left as t minus 2 times t minus 3. So it looks like at 2 seconds and then again at 3 seconds, the ball is going to be at 96 feet above the ground. Now, what is the velocity of the ball at those 2 times? Well, I've got the velocity function calculated, and this is a function of time, right? So I would just plug 2 into that function. 80 minus 64 is 16. Now this velocity function measures how the position function is changing over time. The position of the object is in feet, the time is in seconds. So feet per second, I'd want to make sure that I include that when I give my answer. That would be the velocity of the ball as it's going upward. Okay, now at 2.5 seconds, it's going to now change direction and then head back down. After 3 seconds, it'll pass that 96-foot marker for the second time, okay, as it's going down. And what's the velocity at that moment in time? Well, if I plug 3 into the velocity function, 80 minus 96 is negative 16 feet per second. Of course, one thing that you can notice about this function is that it's a parabola, and one feature of a parabola is that it's symmetric on either side of the vertex, right? So these numbers are just opposites of each other, okay? But of course, the negative would indicate a direction that it's going down, okay? And of course, we've already talked about, velocity of an object, or the instantaneous velocity. That's just the same thing as the derivative of a function. So I don't feel like there's really nothing new in that problem. Okay, problem 18 was just another one that I wanted us to look at, and then I think we'll move on here. So problem 18, it says that if a tank holds 5,000 gallons of water, which drains from the bottom of the tank in 40 minutes, then Torricelli's law gives the volume V of the water remaining in the tank after t minutes as that function that you see there. V is a function of time t. T is ranging from 0 to 40. Okay, we're going to find the rate at which the water is draining from the tank after 5 minutes, 10 minutes, 20 minutes, 40 minutes. Okay, and then at what time is the water flowing out the fastest, and then what time is it flowing out the slowest? All right, so we have our function given here, which is the volume of the water in the tank at time t. Now, as time goes on, there's going to be less water in the tank. Okay, at time 0, you got 5,000 gallons of water in the tank. Now, the volume is changing over time. Okay, in this 40-minute time span, there's going to be less water in the tank. Because the rate of the volume is changing over time, that means that I want to be working with a derivative. Okay, I'm working with a rate of change. So let's calculate V prime of t. That'll be a chain rule. I'm going to bring down the power of 2. I'm going to leave 1 over 40t alone. That'll be to the first power now, and then multiply by the derivative of 1 minus 1 over 40t. That'd be negative 1 over 40. Okay, and if you simplify, 10,000 divided by 40 is 250. Negative 250 times 1 minus 1 over 40 times t, that would be the derivative there. Okay, now it says in the problem, find the rate. Okay, so I'm working with derivative. Find the rate at which the water is draining from the tank after 5 minutes. Well, let's plug it in and simplify, right? So if I plug 5 into V prime, I get negative 218.75. And that's an exact, by the way, so I'm good with the equal sign there. You're looking at how the volume is changing over time. The volume is given in gallons. The time is in minutes. Okay, so at 5 minutes, the rate is changing at negative 218.75 gallons per minute. Okay, how is it changing at 10 minutes? Well, if I plug in 10, 10 over 40 is 1/4. 1 minus 1/4 is 3/4. Negative 250 times 3/4, that'd be negative 187.5 gallons per minute. How about at 20 minutes? When t is 20, you get 20 over 40 is 1/2. 1 minus 1/2 is 1/2. Half of negative 250 is negative 125 gallons per minute. How about at 40 minutes? 40 over 40 is 1. 1 minus 1 is 0. 0 gallons per minute. That should make total sense to us, right? After 40 minutes, the tank is now empty. So there's no more water left in the tank. It's changing at a rate of 0 gallons per minute. Now, they weren't asking for it, but V prime of 0, okay, if I were to plug 0 in, I would have negative 250 gallons per minute. Now, you can see that as time goes on, the rate is changing. This is not a constant rate at which the water is leaving the tank. As the tank empties, the water flows out the fastest at the beginning and then the slowest at the end. Okay. That's all I had in this section. I only had 4 problems that I wanted you to look at on page 233, so go ahead and take a look at those for me.